Hello everyone, welcome to Mayo Programming Club. Today we will be solving another daily report challenge, and the challenge name is 01 matrix. So given a m cross n binary matrix met, return the distance nearest distance to the nearest zero cell for each cell. The distance between two adjacent cells is 1. So what we have to do is, let's take this example. These are rows and these will be columns. We have to tell what is the distance of the let's say for this cell we have to tell what is the distance of this cell to the nearest zero cell. So this cell itself is a zero cell, so the nearest distance of this cell to the zero cell is 0. Nearest distance of a cell to cell. What I mean by zero cell is a cell containing 0. So we have to tell that. For example, all the distances of these zero cells will be 0 since they are 0. So the distance of these cells to the nearest zero cell to nearest zero cell will be 0. So these all will stay 0. This will stay 0, this will stay 0, and this will stay 0. The question arises when the value of the cell is 1. Then we will check for what is the distance of the current cell. Let's say this is the current cell and it is having value 1. And what is the distance of this cell to the nearest zero cell? So all these are the nearest zero cells. We can move to the adjacent cell in 4 directions, which are nothing but left, right, up, down. Left, right, up, down. I hope you are able to understand this. So we have to tell the what is the minimum distance for this particular cell. So in total there will be m cross n cells. M is here the length or say rows, or and here is the number of columns. So in total there will be m cross n cells. So cell, for each cell, you have to tell distance of that cell to the nearest zero cell. What is meaning of zero cell? Cell containing 0. For each cell, you have to tell its distance from nearest 0 containing cell. I hope you are able to understand what the problem statement is asking you to find out. Now let's quickly move towards the constraint. So the number of rows will be m, number of columns will be n, and m and n will be lying in the range 1 to 10 raised to power 4, across n will be of order 10 raised to power 4, and each of the entry in the matrix will either be 0 or 1. And it is mentioned that there is at least one 0 in the matrix. So let's say the matrix is completely filled with ones and there is no 0. So all of the ones will be at infinite distance from the 0 cell. Since there is at least one 0 cell guaranteed, so the distances will not be infinite. So I hope you are able to understand. The maximum distance that can be is of order 10 raised to power 4, which is the number of cells. Now, what is the maximum distance that can be? Maximum distance for a cell. What is the distance being talked about here? Distance from the nearest distance of each cell from the nearest 0 containing cell. Max distance for each cell will be of order 10 raised to power 4. So for checking the maximum distance, let's say we keep a max distance threshold and we add, let's say, 1 to this value. So it will be this. Or say you can add 4 also. That's up to you. One would suffice, but if you want to add anything else, you can also do that. Basically, why I have taken this maximum distance is we will be checking for the boundaries. Let's say if we want to move outside of this cell, then it will be out of the boundaries of the matrix. In that case, we will be denoting such cases with the maximum distance. Why we are not taking maximum value of an integer? Because when we add, let's say, max value of integer, when we add 1 to it, it will not give us correct answer in bounds of an integer. It will be something negative. So that's why we are taking this max distance to be 10 raised to power 4 something. So I hope you are able to understand. Now let's consider a brute force way to solve this problem. To the image. Let's say you are at this cell, the cell with value 1. Then how can you move from this cell to other cells? Or how could you have landed here? You could have came from here, or from here, or from here, or from here. From basically from all the adjacent cells, you could have landed up to this cell. Landed up in this cell, and so there will be 4 possible directions to check for each cell. For each cell, possible directions. Or say 2 raised to power 2 possible directions. So, and what are the number of cells, maximum number of cells? They will be order of n cross n, which is n raised to power 4. So in total, there will be 2 into 2 raised to power 2 raised to power 10 raised to power 4. So these many number of operations will be required if you decide to do it in a brute force way, checking for each cell all the possible four directions. Because let's say you are at this cell and you decide to check what is the nearest zero. Then you will check in this direction. You will go in this direction. Let me quickly change the color here. You will go in this direction, go in this direction, go in this direction, and in this direction, all four directions of adjacent cells. And you will be checking among all these four directions, which direction is giving you the minimum distance of the zero containing cell. So in total, these number of operations will be required, and these operations are very much greater than 10 raised to power 8 operations. Allowed in 1 second. Basically, what happens if the number of operations of your program solution or say program exceeds or become equal to 10 raised to power 8 operations, then you may get a TLE, time limit exceeded, and your solution will not be accepted. So those of you who are not familiar with this concept, I will be providing a link describing how the complexity of accepted solution varies with input size. You can explore this article and then you will be able to understand what we are talking about here. When your program's number of operations exceeds or become equal to 10 raised to power 8 operation, then you may get a TLE. So in order to get your solution accepted, you have to optimize this brute force. Now let's say we decide to optimize the brute force. Now consider this cell only, which is containing 1. Now, if you are presently at this cell, you could have moved from this cell, or you could have moved from this cell, or you could move from this cell, or you could have moved from this cell. So, whichever value will be the minimum, what is the value being talked about here is whichever adjacent cells will give you minimum distance from zero containing cell. You will consider that choice or adjacent cell. You will consider that choice. Yeah, or say adjacent cell. And you will add 1 to it. Since moving to this Let's say from this cell to this cell will require you 1 unit of distance. It is also mentioned in the problem statement also. The distance between two adjacent cells is 1. So you will require 1 unit of distance to move from all these cells to the current cell. Let's call these four possible cells or neighboring cells or previous states. Current cell will be current state, and previous possible cells will be previous states. So what we will do is, let me clear the board out. Yeah, it's clear now. So let's proceed. So first we will be checking for these two directions. We will be filling your, let's say this is the distance board representing the distance of each cell. Representing distance of each cell nearest zero containing cell. Let's say this is the distance board. Then how you will be populating this board? Let's say you will be going from top to bottom first. And you will be checking for these two options for each cell, which will be the cells in top to bottom approach. Let me quickly change the color here. Top to bottom. These are the approaches to fill the board. Approaches to fill distance board. And another will be from bottom to top. For the top to bottom approach, you will be having two options for each cell. For each cell, either you could have moved from the up direction, or you could have moved from the left direction. These two directions I am talking about. This is the upward cell. This is the left cell to the current cell. So these two will be the previous states. So whichever of them is giving you minimum distance from the zero containing cell, you will take them. So you will take minimum of both of them and add 1 to it, since moving to this cell would be requiring 1 unit of distance, or say 1 unit of work. Same for this. So we will be taking the minimum of these two options and adding 1 to it. Similarly, for the bottom to top approach, once we are done filling the board in this way, top to bottom approach, in this approach, it will be from down to, let me change the color quickly. It will be from either from downside in this side or from right side this side. So these two will be the options, and you will be taking minimum of them, and you will be adding one because this much work will require us to transition from either of them to the current state. These two will be the previous states. So once you have taken minimum of them, then you will again take minimum with, let's say, let's call this distance board, or say simply distance. This is distance board. Let's say for r comma c coordinate, r is the row number and c is the column number. You will be taking this distance value would have been populated or would have been given a value in this top to bottom approach. So you will take minimum with this also. What I mean to say is, let me clear some space out so that I can write there. I think here I can write. So what you will do is distance of RC in case of bottom to top I am talking about. So it will be minimum of distance RC, minimum of 1 plus minimum of distance R plus 1 C, distance R C plus 1. This is nothing but two options that we are having either from this downward direction or from the right direction. This is for down, this is for right, and this is to make transition. So in this bottom to top approach, distance of a particular cell will be looking like this, and is in case of bottom to top approach it will be top to bottom, distance of RC will be 1 plus minimum of distance of R minus 1C, comma, or colon, distance of RC minus 1. This one is for up direction, this one is for left, and this is for transition. Transition is basically moving from one cell to another. So this will be it. And at last, after doing these two approaches, after you are done with first, you can pick any of them to be the first approach. I have just picked top to bottom to be the first approach. So it would not change your solution in to very large extent. So after doing with these two approaches of filling the board, after being done with these two approaches, of filling the board, we will return the final distance board. So this is how you will be solving. Now you may ask why we are storing the results of the previous states. Because our problem was having two conditions which can be used to apply this kind of solution, and this kind of solutions are called dynamic programming solutions. So let's say there is a problem, bigger problem, and then it can be divided into sub problems. Let's call this sub problem 1. Let's call this SP for sub problem 2 and SP3 sub problem 3. To find the solution of, let's say, this bigger problem, let's call solution as solution big. What you will do is you will find the solutions for the, if you can find the solutions for the smaller problems, let's call this solution 1, solution 2, and solution 3. If you can combine these solutions and form the solution for the bigger problem, this, then this type of property is called optimal substructure. And another property should be satisfied in order to apply this dynamic programming, which is nothing but storing your result. For previous states. Now, this second property will answer why we are storing this result for previous state and how this will be helping us. So let's say somewhere while discovering for a minimum distance for a cell, let's say 4,3, you somewhere ended up checking this cell 2,1. If you, let's say, take the right direction. Now let's say you take left direction, and after some set of choices you again landed up at this cell. Now you can see that for this particular cell you will be doing work checking this distance to the nearest zero cell for this particular cell, or say state. You will be doing calculations more than once. So in order to avoid these calculations being done more than once, what we will do, we will just store the result of this state. R here will be 2 and C here will be 1. So we will just store it, and whenever we will encounter this state again, let's say for the first time we calculated the answer, we have done the calculation. Then for the second time, we will just return this, return distance of 2, 1. So that's how we will be saving our X tower. This is nothing but saving the X tower. And this is, let's say this is the current state. Let's say this is the previous state. As you can see, the solution for the current state, let's call this solution current, is depending upon the solution of the previous state. Solution previous. So these two are related. So once you have found the solution for the previous state, you can build the solution of the current state, which is nothing but this property. For each a bigger problem, you can divide it into sub problems and combine their solutions and find the solution for the bigger problem. So this property satisfies, and this particular property of calculating same state again and again is called overlapping sub problems. If these two property are being satisfied from the approach you will be taking, then you can apply this dynamic programming approach, which is nothing but storing the result of the previous states and then building solution for current state from, let me quickly clear the board. Current state from solutions of previous states. So that's how you will be finally building your final solution, which is the solution of the biggest problem. And so yeah, that is the approach that we have taken here. Now let's quickly move towards the coding part without further delay. Let me quickly zoom out so that the larger portion of code is visible to you. So what we have done is we have this distance 2D array will be returned as result. This 2D array will be returned as the result, and each cell in this array represents a state which is nothing but the coordinates r comma c. So we are calling this a state. So this is we are filling the 2D array distance. This is we filling the 2D array distance in top to bottom manner to account for the choices of upward and left cell to the current cell being checked for its distance to nearest cell containing 0. So based upon two previous states, uh, this is for the upward direction, and this one is for left. And we will check the boundaries. If your move would make you to go outside the boundaries of the board, then you will be giving maximum distance, otherwise you will be giving this distance. Similarly for the column part also, you will be checking whether we will be in the boundaries when we will be making this transition to the uh, current state to the previous states. So I hope you are able to understand. This is just a boundary check, and accordingly we are deciding what value we will be returning. We will be taking minimum of previous test distance and adding one to it. One is for transition, and similarly we'll be filling the board in. Then we will fill the board in bottom to top direction to account for downward and right process, which could have led us to the current state. State here is nothing but a cell or points. So it is pretty much similar with a little difference that we will be checking the previously populated distance also. And at last we will be returning the distance node. So let's try to quickly submit it. It's working fine, as you can see. So what will be the time complexities and space complexities? Time complexity will be order of m cross n, which is the number of operations will be 10 raised to power 4, which are lesser than this 10 raised to power 8 limit. Your solution will be getting accepted. In the space complexity, it is also m cross n to store the distance for distance body array, which is of order, which will be 10 raised to power 4 maximum, this m cross n. So these are the complexities. Now, if you are still having any doubts, please feel free to ask them in the comment section. So thank you for watching. Thanks.